Welcome to the DP Aliens trick lecture. This is one of the more complicated tricks in Platinum, and much more complicated DP tricks. It's called Aliens trick, named after the problem from IOI 2016 called Aliens. So you can go check out that problem after the lecture. For this problem, we're going to solve a slightly simpler problem which uses Aliens trick, but it's still pretty complicated. So this is the problem in the chat. It is a Div 1E problem. Difficulty 3000, so probably on the harder side, but with Alien Trick, it actually becomes a lot easier. And you can actually, the value of n is 2000 in this, so you're probably expecting an n squared log n. If you apply Alien Trick correctly, you can get an n log squared n, so much faster than the intended solution for a Div 1E, which is pretty incredible. And yeah, so I've seen this problem, I've seen this trick show up in quite a few contests, so it's pretty useful to have. Okay. I put the problem in chat for you guys to read. I'm also going to share my screen with it and then be quiet for a moment to give you guys a chance to actually read it. All right, so let us get into it. Hopefully you have had a chance to read the problem. So let's first start with a simple DP that would make sense here, right? So just to sort of recap the problem, there are n Pokemons, and if he throws a Pokeball, he catches it with probability P of I. If he throws an Ultra Ball, he catches it with probability U of I. And he has A Pokeballs and B Ultra Balls. So, and he can throw both an Ultra Ball and a Pokeball at it, but he can only catch it once. And you try to maximize how many you can catch, given the restriction on the number of Pokeballs you can throw and the number of Ultra Balls you can throw. All right, cool. So, what would be a basic DP for this? You might say basic DP would be index A thrown, B thrown equals max. So we're trying to output the maximum number of expected Pokemons you can catch. So it just makes sense for this to equal to the max possible expected Pokemons. Gasha can catch. And for transitions, you have several options. You can not throw either. We can throw something of type A. We can throw something of type B. Or we can throw A and B. All right, and when I say throw A, so we have like A Pokeballs, right? So I'm just going to say throw a Pokeball. For throw B, we have B Ultra Balls. This just means throw an Ultra Ball. So basically, we're using one of like B thrown and one of A thrown. So I think using the words Ultra Ball and Pokeball are a lot harder to think about than just thinking about using Pokemon or using A and B. All right, so if we don't throw either, then we're going to have DPIJ equals, or let's put this way. DPIJ equals max of the 4 cases. So the case if we don't throw either, then our previous state is going to be DPI minus, DPI, let's call it AB. So 2 states here. So we're going to be DPI minus 1 AB. If we throw something of type A, our previous state is DPI minus 1 A minus 1B. If we throw something of type B, our state is going to be DPI minus 1 A B minus 1. And if we throw both, or sorry, I should slow down for a second. If you throw something of type A, our previous state is going to be DPI minus 1 A minus 1B. Then we also have to add the expected number of Pokeballs that are going to be updated. So it's going to be probability A. Probability that type A catches ball I. This is going to be the probability of type B catches ball I. So I'm just going to slow down for a second because I got a little bit ahead of myself, got excited there. So we don't throw either. It's just, previous index, same number of A and B. If you throw something of type A, its previous index, you're throwing 1 fewer of A, plus the expected benefit that we get for throwing something of type A. For throwing something of type A at the ith index. So we're throwing something of type A at the ith index. We're throwing type B at the ith index, that's that. If we throw both A and B, It's going to be dp I minus 1, a minus 1, b minus 1. Plus, we want to add the probability that either A or B catches the Pokemon. But we want to make sure that I see a comment in the chat. I'll come in a second. But we want to make sure that we don't consider the case where both of them hit the Pokeball. Like we only count it once. So we don't just want to add this and this because if both of them hit the Pokeball, we only want to count it once. So there are a couple of ways to calculate the probability that A and B. Probably that either A or B hits I. And there's a couple ways to calculate this probability. The probability that A or B hits I, you can do probability of A. Probability A hits I plus probability of B hits I. And then subtract out the case that they both. So subtract out the product of them. Another way to calculate probability of that A or B hits I is going to be 1 minus the probability that both of them hit I. Or sorry, 1 minus the probability that neither of them hit I. So it's going to be 1 minus probability neither hit I, which is going to be 1 minus PA of I times 1 minus PB of I. Those are the couple of different ways to calculate the probability that either A hits I or B hits I. Okay, shouldn't you multiply probability? What do you mean by multiply probability? Do you mean it like for this part here? Might be clear if it's in parentheses. Like what probability you're trying to multiply? Rather than anding in transitions? I'm not sure I follow. Can you explain this a little bit more? Ah, I see what you're saying. Okay, so let me just copy this here so that other people can see it as well. So he was asking why we don't do this transition here, right? PB of I times DP I minus 1 AB minus 1. And the reason is every single Pokeball we throw at every index is independent. So when we throw a ball B at index I, it doesn't affect any of the previous ones that we threw it at. It only affects index I. So, got it. Perfect. All right. Okay. So this is going to be our base transitions, and our runtime for this is going to be O of n cubed. Right. And that's going to be a little too slow for this problem. So, for this, we are going to use something called Alien's trick. Now, this is where it gets kind of fun. So, the first observation we can make is, let me draw this out. Okay, so let's say that we've decided to throw something of type like A here. We've thrown A and B here. We've thrown like nothing here, maybe like B here, maybe like AB here, maybe like B here. Something like this. So here we have B equals 4 and A equals 3. Okay. Question for everyone here. Let's say that someone comes in and they're like, ah, B is going to be 5 now. So B increases by 1. Do we change the location of all these B's here? Or are we simply going to add 1 B to a new location? Like, is there a reason that we would say remove this B and add a B here and here? Or would we simply add a new B somewhere else? Okay, I'm seeing add somewhere else. Another somewhere else. Okay, about half of you answered, which is probably good enough. Yeah. So we're actually going to add it somewhere else because let's think about this. let's say we decided to delete this B from here and put a B here and here. Well, wouldn't it have been better to never put a B here in the first place and I put a B here in the first place if that was true? Like, why was is this location not good enough before, but it's good enough now? Or sorry, it's good enough before, but not good enough now. Like, what just happened? Now there's a second case of like, what happens when we have a B that's part of an AB? Would we want to remove this and put it like here and here? The answer is clearly no, because like, why is this AB good now, but it was like, this was better earlier? Something's like off. What if we replace this B here with like a B here and a B here? This is the interesting question. And here's the deal. If this B location was better than the B here with an A, we would have placed a B here in the first place. So every time we add a new B, or if A were to go up to like 4, every time we add a new A, we're going to keep our same answer and add the new thing somewhere else. It's an interesting observation. You might say, Ria, how does this speed up our DP state? Nothing yet. Just make some observations that are going to get us there in Alien's trick. So, what this means is that the benefit that you get every time you add a new ball of type B or you add a new ball of type A decreases. So, like, for example, like our answer, that's in white. Let's not use white for that. Let's say our answer, if we have like A equals 3, or we have a given like A and B. So let's just say we increase B plus B by 1. So our answer, this difference, right? This difference is basically saying the amount our answer increases when B increases. We're saying that this value is going to go down each time. So this value is going to be greater than or equal to the difference if we go from B plus 2 to B plus 1. So every time we add a new B, the amount our answer increases keeps going down. Okay. Gonna pause here for a second. Any questions about this? Okay, wonderful. And if I like say wonderful too fast, feel free to keep putting questions in the chat and I will keep getting to them. All right. So we talked about DP optimizations in the previous lecture. And, we said that like the runtime of a DP thing is going to be DP of a number of states times number of transitions times runtime per transition. So if the number of states is n cubed, our runtime's never going to be faster than n cubed if we're going through all states. So this means that we have to remove one of these states. We just do. So what we're going to do is we're going to try to remove one of these states. So we're going to say, what if we just do DP index 8th row? And we're going to make it equal to the max expected Pokemons, given that we don't throw more than a B of type B. This is using the letter B twice, but I'm sure you know what I mean. Like the max number of Pokeballs, given that we don't throw more B than type B. Make it a little bit brighter. There we go. So we just completely destroyed the B index. But these makes our transitions break, right? Where we're using the B index to make sure we don't exceed the constraint of type B. Usually for constraints, we'll put a constraint in as like a state, and that's what we're doing here. So what do? Well, notice this property that we had earlier, where we said every time we add a new ball of type B, the benefit decreases. So what if I say we're only going to take balls of type B such that the benefit we get from the ball is greater than or equal to some capital C. So, we'll figure out the A dimension will happen as it happens, but we're going to say we're only going to throw something of type B such that the benefit we get from the ball is going to be greater than or equal to C. Okay. So how do we do this? Well, let's just calculate what our dp would be, right? And then we'll go a little bit from there. So if we don't throw either, our new dp is going to be dp IA. If we throw something of type B, this one type A is actually pretty straightforward, right? A minus 1, or sorry, it's going to be I minus 1A. It's going to be I minus 1, A minus 1, plus probability, okay? Okay, what happens if we throw something of type B? It's going to be dp I minus 1A, and the benefit we get is going to be PB of I, but how do we ensure benefit we get is at least C? Well, we're only going to do this if PB of I is greater than or equal to C. And don't worry about how we find C now. Let's just assume a magic genie is telling us this value of C that makes our answer valid. So the magic genie is telling us the value of C that gives us the right answer. Okay. This is pretty pretty straightforward. Now what happens if we throw both A and B? So that's going to be dp I minus 1A. The benefit we get, what is the benefit we get? Sorry, plus PAB of I. But how do we ensure that the benefit is at least C? Because they're throwing two of them. So we're only going to do this if P of A of B of I minus P of A of I is greater than or equal to C. So the benefit we get for ball B is going to be the added benefit we get after having already thrown ball A. So we subtract out P of A of I. Okay. So this is basically it. That's basically it, with the exception of how do we find the value of C? So how do we find this correct value of C? Well, the answer is we can simply binary search on the value of C. So we can binary search on the value on the benefit that each of these is gonna give you. So we can binary search on C from 0 to 1. And how do we check if a given value of C is valid? Well, a given value of C is valid if the number of times we take a ball of type B is less than or equal to the constraint of capital B. So we're gonna do our DP normally. We're just gonna keep track of a counter, which is the number of times we've taken a ball of type B. Cool. All right, I'm gonna pause for a second. Any questions about this? Awesome. Now, a really easy way to implement it is instead of doing an if statement check, because you're just taking the max of these green values, right? We can just say dp I minus 1A plus P of B, and then we can just do minus capital C. Now we don't have to do this check, because if PB of I is not greater than or equal to C, then this value here would be negative, and our code would prefer to take this state. So if it doesn't give us a benefit of at least capital C, we're just going to take this transition here instead of this one. So this ways, we don't have to do an if statement check here, And same thing here. We can just do minus C. And that way, if, this value isn't at least P of A of I, then it's going to take this transition instead of this transition. So if the benefit that ball B gives us is not at least C, it'll just take this transition instead. So we can delete this. And now our answer is going to be dp n a plus C times B, because we have subtracted C for every ball B that exists. This is actually the cleanest way to implement it, because you might find that, like, let's say we're implementing it and we run into a case here where, like, the benefit that something gives us is going to be like 0.2, 0.2, 0.3, 0.3, and we get like capital B equals 3. So when we do our binary search says, okay, we're going to take things that give us, well, if we take things that give us greater than or equal to benefit of 0.2, oh no, this is not going to work, because we're going to take 4. It's going to be too many. So our binary search is going to say we're going to take things that give us a benefit of greater than or equal to like 0.200000001 or something. So it'll only take these two, and then you have to say that, like, the benefit for the remaining ones that we're not really taking is because it equals C. So we're going to add C times the number of type B that we're not actually taking. So it's just cleanest to implement it this way here. All right, any questions about this problem? Great. Clear. Wonderful. All right, so now our runtime is going to be log 10 to the power 9, because actually log of, like, whatever you're doing to figure out this value of C. So log of the benefit that you get, which is basically like 2 times n. We just have to, like, try all possible values. Like, the possible values of C that we care about are ones that distinguish, like, for example, in this problem, there's 4 values. If we need to try C's in between possible benefits, so it's going to be log of n. Times n squared. And this will run in time. Now, if you're like me, you then decide, there's a way to do this faster. And that's just interesting to do it faster. We can apply the same technique we did to remove the dimension of B. We can apply it to also remove the dimension for A. We can apply Alien's trick a second time to also remove the dimension of A. So we're only going to take a ball of type B such that the benefit we get from the ball is greater than or equal to C. So now we're going to add a second variable D, and we're taking the balls of type A that are greater than or equal to capital D, and we're going to binary search on D, and for every value of D, we binary search on C. This is a little bit complicated, so stick with me here. Let's pick a different color. And if you don't understand this part, that's okay. This part is a little bit more complicated than typical Alien's trick. It's just a bonus that I'm adding in, knowing that it might be a little complicated if you've never seen Alien's trick before. So this is more so like if you've seen it before, if you're comfortable with it, you might follow this better. But if you're not following it, don't worry about it too much. You can come back and see the recording later once you get familiar with the first Alien's trick. So all right, so if we don't throw either, it's just going to be DPI. Oops. If we, sorry, DPI minus 1. If you throw something of type A, it's going to be DPI minus 1 plus PA of I minus capital D. If you throw something of type B, it's going to be DPI minus 1 plus PB of I minus capital C. And if we throw something of throw A and B, it's going to be this plus P A B of I minus C minus D. And our answer is going to be dPn plus D times A plus C times B. And what you can notice is that this actually becomes a greedy. Like GP I minus two previous DP states aren't used at all. You can just greedily take the best between 0, this value, and this value. So this is a little more complicated to think about, obviously. So essentially we're gonna like a binary search on D. And inside the binary search on D, we're gonna do a binary search on C. Now, when we binary search on C, we have to make sure that we don't care about the value of capital D at all. Okay, when we binary search on C, we calculate the amount of A taken and B taken. In the binary search on C, we just calculate the amount of B taken. And if it's too few, we're going to decrease the value of C and we're going to start taking more. If it's too high, we're going to increase the value of C. In here, we do not care about the value of D. Do not care about that. We do not care about the number of A taken. We don't care about anything related to A inside this binary search. We're binary searching on, like, once we have a value of C that works, then we do the check on D to decide if D has to go bigger or smaller, and then we repeat the binary search on C. All right, any questions about this part? I know this part's a little bit more complicated, so any questions on how do we add the second binary search? And now our runtime is going to be n log squared n. All right, perfect. So if there are no more questions, then what I'm going to do is I'm just going to walk through my code for the binary searching on C and D a little bit, because that is a little bit more complicated. It was very tricky to like make this code super readable, but I think I did sort of a decent-ish job here. So, all right. We're reading the probability of A, probability of B. We calculate the probability of A, B. Great. Now we do our binary search on D. So while they're different, this is just to debug. So we calculate the mid value. If the number of B's is too high, we're going to decrease the value of capital D. If the number of B's is too low, we're going to increase the value of capital D. And this just like prints the answer given a value of B. Oh, sorry, if it's too high, we're going to decrease the value. If it's too low, we're going to increase the value of D. So D is the cost that we accept, right? So if we count and we have too many, we're going to up the cost. Otherwise, we're going to lower the cost. So notice that in this loop checking for B, we do not care about A at all. Now, in this count D function, that's the only function that's being called, count B. Let's go to it, count B. So here we're going to binary search on the value of capital C. And A just means lower bound, B means upper bound. So capital C lower bound, capital C upper bound. So we're going to count the values, count how many times A is taken for a given value of C. I think I might have switched C and D for my explanation between here, so don't worry about that too much. Anyway, so we're going to be given a value of the D and a value of C. We're going to count the number of times A is taken, and we're going to update C. And then we're going to return the number of counts. Count A returns a pair of like A and B. So if the count, like the first one is A, and the second one is B. It's that straightforward. Perfect. Any questions about this here? Wonderful. All right, so that's all I have for you today. What I'm gonna do is I'm gonna give you put the problem in the chat for the aliens problem that this trick was originally designed for. I think the problem that we worked on today is a little bit cleaner application than the aliens problem, but that's okay. It's basically the same thing. Cool. Oh, sorry, one more thing to go over in my code that I forgot we did. We forgot to like the actual counts of counting A and B. That's going to be here. So our options like to actually count. We take neither. We take A, so we subtract C. We take B, and we take both. The exact same transitions we did. If this option is take neither, we don't update the number of times we've taken A or B. If option 2 is the best, we're going to take A. If option 3 is the best, we're going to take B. If option 4 is the best, we're going to take an A and B, and we're going to return how many we took. And then our answer is going to be Right, the answer plus C times A plus D times B. All right, wonderful. Well, if there are no questions, then that is the entire training I have for you today. I hope you will now be able to see aliens trick and problems that you just do on a regular basis. It's not a super common trick, but it does show up every now and then. And when it does show up, if you're not familiar with it, you're not supposed to get the problem. So knowing aliens trick is essential whenever it does show up. And I've seen it show up in quite a few problems here and there. Thanks for attending, guys, and I'll see you guys next week.